So there were a couple of students who were asking advice on the last week's exercise. And as I previously discussed, these kind of courses which are already more or less advanced level, I don't share the step-by-step solutions online, partly also because of the reason that the instructions are more or less given in the lecture material. If you follow them carefully, you can duplicate the calculation by your own. But the more important reason being that if I put this kind of calculation result there, it's far too easy just to copy it without thinking what to do. And of course, it is fully possible to copy a calculation and learn while you think, but it's difficult to make sure that everybody's doing that. So therefore, this approach and more or less this machine elements is already applying something you already know. So we don't need to learn any new sort of ways to think, for example, mechanics, which is far more difficult, like in basic courses. We are more or less just using different equations, using different tables and the previous knowledge. And therefore, it's possible to do it by your own following the lecture material. But here is the calculation for last time exam. As again, I did also myself a mistake in it. So thank you again, Mr. Tirkkonen, for correcting me. So maybe I should start giving you some salary for checking my calculations. But now it should be correct, and the values have been updated to the model already last week. But here's how the calculation proceeds. So you have a machined round bar, which is subject to, firstly, completely reverse bending, meaning R2 minus 1, and a constant tension. So the bending with the capital M and the constant tension with the force F. And as you know now from previous knowledge from mechanics, hopefully, you can see that this amplitude for the stress is only coming from the bending, because the bending is the only one which is fluctuating. And the tensile force is constant, which means that the tensile force is causing the mean stress. So the mean stress is coming from the tensile force only, and the amplitude is coming from the bending moment only. That is the trick in here. And further on, we know that the material has been tested for 800 megapascals of ultimate strength. And when we follow this approximation for fatigue limit, which was for steel materials with less than 1400 megapascals of ultimate strength, we can use 50%. So therefore, for a smooth unnotched component, we can assume that the fatigue limit for zero mean stress would be 400 megapascals. And if we would only have now the loading with the bending moment amplitude, so there would be no constant tensile force, we could just use this value, with of course with a combination with the reduction factors M. But if there was only bending moment amplitude, it means that we would have zero mean stress, because it is fluctuating on both sides on the zero line. But now, because we have this constant tensile force, that will create us mean stress, and that we will need to take into account with the Goodman equation. So firstly, we will define the notch factors that is already known to you, and eventually the fatigue notch factors with a different kind of loadings. There's also torsion here because the template has been used for other tasks as well, but we don't need torsion here. And these are the values I showed in the Moodle already. And now we can calculate the stresses, and as I explained, the mean stress is now only due to the constant tensile force. So only the tensile force is causing the mean stress now, because the bending moment amplitude is fully reversed. And when it's fully reversed, it means that the mean stress is for that in zero.
So it compensates itself.
More or less, you could say. So and that is the common case for rotating machinery. So in this case, I didn't say that it's from rotating machine, but it could be. In a rotating machine, it's usually the case that you have, for example, gravity load. There is some like a coupling or some large pulley or whatever hanging on the shaft end, and that is bending the shaft end, of course, towards the earth from the gravity. And due to the rotation, the direction of the stress in the shaft is changing, which means that the in the start of the rotation of the shaft, the bending is at the top and the compression at the bottom. But while the shaft is rotating, the point from the top of the shaft is turning aside, and after half turn, the same point would be in the lowest point, in the 6 o'clock position. And in that point, it would be in the compression. So this way, a rotating shaft, which is under gravity load, will experience fully reversed bending loading. Did you get what I mean?
Yes.
Sorry, can you say that again?
Maybe it's better that I'll share the drawing table. I'll try to draw it.
So will it be true that in with shafts we can just neglect the bending stresses?
No, we cannot neglect it. No, it doesn't mean that. But it means that the bending from gravity load in a rotating shaft, it is always fully reversed. It means that there's no mean stress from the gravity load in a rotating shaft.
So it's only applicable for mean stress, not to all stresses. For example, if we are calculating for Mise, then we are taking into account the bending as well.
And now I'm not sure if I fully understood what you mean. If we are calculating the von Mises, we have to calculate all of the components which they are existing. But if you only have gravity load in a rotating shaft, you would only have plus and minus bending, nothing else. So you don't need von Mises for that. But of course, usually there's a torque induced also, so you would need to include the torque in the von Mises, so you're right about that. But if you can see the screen now, I'll draw the same picture I draw already last time in the lecture.
We only see your whiteboard and your mouth is not moving. Oh, no, it's moving, but...
Yeah, why doesn't it show?
Nothing is drawing.
It's not drawing. Why?
We had the drawings before, but then it just vanished.
Yeah, because I took the new page for it, but I was drawing in my drawing, but now it's coming.
Okay, now it's drawing, yeah.
Yeah. So here is the shaft, like that. Okay, and you know that if we have gravity bending, it will mean that we have stress distribution like this, right? Say yes in your mind.
Yes.
And that will mean that here we have tension, and here we have compression. Right?
Yeah.
And now, when we have the gravity is always acting downwards, and consider that we have here point 1. And now we look the shaft from here. And we see that the point number 1 is here. But now when the shaft rotates, it means that eventually the point will end up here. Right.
Mm-hmm.
And now, because the direction of the gravity is in the same direction, it will mean that in this case, in this situation, in this position of the shaft, point number 1 will see compression. Right.
Yes.
And that is the reason. So the stresses.
I'm sorry. Will it be the downwards if the point is in the down position? Would be compression, not tension? Like it doesn't work for me. I didn't get it. Why it would be in compression?
Because when you think that you bend a shaft like this.
Okay, from the okay, now I get it. Yeah, okay, thank you.
So if you have this kind of configuration and you press it with a force like F, here will be tension.
Tension, yeah, and the other side is compression.
And here
yeah.
compression, yes. So thus stress varies in point 1 between compression and tension. And this absolute value is the same. So here we have here is tension, so it's plus bending, sigma bending, and here it will be minus sigma bending. Equal value. So therefore it is fully reversed.
So just to make it clear about the mean stress, so we use mean stress in oscillations, in stress oscillations, so to say, to define like the average stress. Or am I wrong?
Well, the mean is the one which is the middle of the oscillation. So in this case, if you would only have this load case, it would mean that the mean stress is 0, right? Because it's varying between plus and minus the same value.
Yeah, so mean is just mean like average.
Yes, the average here is the center, that is 0 right here. But axial constant force F is introducing mean stress now. because let's draw it again. Now we have this axial force F, and the distribution is, of course, evenly distributed. All over the surface, right?
Yes.
And now when we combine this to here, the complete is that you will have this mean stress portion which is the tension, and that is the mean now because it's in the center. And then you will have additionally the bending, which in the top part of the shaft will increase the tension, and in the lower part it will reduce the tension from the mean stress. You get it?
Yeah.
Yes.
So basically the F, the constant force, is setting the average level around which the bending amplitude is pulsating the stress around.
Yeah, this idea is quite clear.
Okay. So therefore, as we know this now, we can calculate the stresses. So the mean stress now is only due to the constant tensile force, and we can calculate it with a simple equation, force divided by the area, and of course we need to take into account the fatigue notch factor, and that will give us 50.8 megapascals. And we don't have direct shear nor torque shear in this case because we were only having bending, pure bending, and pure tensile force. But of course, if the loading would be different, there could be shear force as well if we had torque, and if we would have vertical forces acting, it would mean that we would also have direct force, direct stress. But now we have calculated mean stress, and then we need to calculate what is the stress amplitude. And the amplitude is now, as described, it's only due to the bending. So the constant tension force doesn't affect amplitude because that is constant. That is producing the mean. And the bending moment amplitude is producing the amplitude. And now that we can calculate that with a simple equation, as you know from basic mechanics. Of course, multiplied with the fatigue notch factor. And now we have these stresses calculated, then we can go on into the reduction factors. That is going exactly as I presented in the lectures. And it a bit depends on the material, what you select from the table for the material. I was using the value for quench and temper steel, QT steel. And eventually I got the value of 0.68 for overall reduction. And then we can calculate this modified fatigue limit for the mean stress, applying the Goodman equation as presented in the material. And further on, when we include the effect of the reduction factors, we can get the fatigue limit, fatigue strength for our case, which includes our situation of mean stress and our situation of ambient conditions, etc., reduction factors. and that would be now 256.4 megapascals. And now simply we can use this as a sort of strength value, which we then divide by our amplitude, which was calculated here. If we would have some other stress components induced, like torque, we would need to calculate the amplitude using von Mises. And that is something you will need to do in your project work. You have to calculate the amplitude and also the mean using the von Mises equation, because there's also direct shear and there's also torque shear. But that's not that much more difficult. You just apply the von Mises equation and you put the correct stress components in the equation, and you will get the von Mises mean value, mean stress, and the von Mises stress amplitude, and apply those in these final equations. And also in this modified fatigue limit. Yes?
So is the difference between this task and our project work is the amount of loads and in the first place, and secondly, instead of well, just simple not normal stress, we use mean stress there.
Yes, you have
in von Mises. Yeah.
Yes, you have to use von Mises for both the amplitude and the mean stress in your project work.
Okay, so we first calculate von Mises and then we put them into the amplitude and the mean stress. Or
no, you are calculating the
vice versa.
Vice versa. So you have to calculate the mean stress von Mises using the components that produce the mean, the stress components that are producing the mean. And then you calculate the von Mises stress amplitude using the stress components that are varying.
Mm-hmm. Mm-hmm.
Sorry, I have
we can,
a question.
Yeah.
You said
go ahead.
earlier that the mean stresses is zero caused by the bending in a rotational shaft, but and I say this shaft is it's not rotational, so why we omitted this the mean value of caused by the
because it's said in the task assignment that it is completely reversed. So basically the situation we have here is as it would be a rotating shaft. But I just already given you the information that it is completely reversed.
Okay, thank you.
But there will be lectures and lecture times for helping you in the project work, so you can ask guidance in that. But the basic process is pretty much here, just that you would need to apply the von Mises when calculating the mean and the stress. So otherwise the process is the same. Which leads us into the discussion about project work. So we could check what is the task assignment. Finally, I think everybody's been quite eager to get this assignment. So can you see the screen, by the way?
Yes, we can.
Okay.
Before we go to the project work, can I add something about the fatigue stress? I have something in mind.
Yes, go ahead.
For the previous exercise, we calculate the stress, the fatigue stress, and it includes the mean of the mean of the variation is affect to the fatigue strength. However, in other lecture, we have cooler graph that they just depends on the amplitude of the stress. So I quite don't understand, like in the calculation that they do affect the fatigue, but like in the graph we just see they are just depend on the stress range, the stress amplitude.
Well, that is exactly the reason that we are using the Goodman. Because the Goodman equation transforms our mean stress plus amplitude such that we can compare it to the Wöhler curve, which has been drawn for only amplitude. So the Goodman equation is used for that purpose. You are right about that. The Wöhler curve is using only amplitude. But in the real cases, like now in the exercise, we have also mean stress induced. And then we use Goodman equation to modify our loading amplitude so that it will give the sort of equivalent result when we apply only the Goodman modified amplitude onto the Wöhler curve.
I still not understand. Like
Okay, maybe it's best that maybe you can put me email and write, read the previous lecture, because there it is stated that the reason we are using Goodman equation is that we can then use the modified amplitude to the Wöhler curve, which is drawn for pure amplitude only.
maybe I should read the presentation again.
Yes, please do it. Okay, but for the project work, your task would be to calculate a main shaft for a 3.5 megawatt wind turbine. So the construction of a wind turbine is as is shown in the picture here. So there's a rotor hub, which is sort of used for hanging or fixing the blades. And after that, there's the set of main bearings, 2 of them, and between those, there's the main shaft. And after the main shaft, there's usually gearbox, and then brake, and then a generator. And when we dimension the main shaft, there are different kind of load cases, many load cases, but now we are only dealing with 2 of them, which are typically the ones that pretty much define the size of the shaft. First one is the assembly of the blade, which is static load case, because that is happening usually only one time in the history of the wind turbine. And assembly of the blade is happening as shown in the picture here, so that the blade is brought into the hub in a horizontal position, which means that this surface over here is directed like horizontally, and then the blade is brought to it, and then the bolts are attached. Then the hub is turned in a way that the next blade interface is in this position, and then the next blade is brought in. And then it's the same procedure for the third one. Later on, we can see what is the most critical situation in this assembly phase. But for that, we need to perform the static load analysis, which means that we will investigate that will the shaft remain unyielding due to the high loads in the blade assembly. The second load case would be operation, and that is then a fatigue load case, of course, because the shaft is rotating and we have some fluctuating loads from the wind, and that will require fatigue analysis. And these 2 load cases you need to define. And what you need to keep in mind while calculating the loads is that the main shaft is tilted. In this case, it's 4 angle. It could vary. Some turbines are only 3 degrees tilted, and some of them even more, could be 6 6.5 degrees tilted even. And could you imagine what is the reason why the turbine like this is tilted backwards?
I think it is to balance the the, the turbine. So there's no stress bending in the holding shaft, and the central gravity is directly pointed at the standing shaft, isn't it?
That's a good guess, but not primarily due to that. The actual
of the weight
reason
of the
is
blade?
that. Sorry?
Because of the weights of the plates or something? You can change the... Yes.
You guessed well. It's because of blades. But if you look a video about the running wind turbine when it's heavily blowing wind, you can see that these blades are bending a lot because they are quite long usually, 50 to even 80 meters long. They bend. And if this angle of the main shaft would be horizontal, there's a risk that the tip of the blade would hit the tower because it's bending that much. It bends meters, several meters, if you measure it from the tip. So therefore this shaft tilt has been done due to that it will prevent the tip from hitting the tower, even though there would be the bending of the blade. You can see some of the YouTube videos. If you see that, for example, wind turbine destruction, you can see that there has been problems with the brake of the machine, so that there's a storm and it starts to wildly accelerate. And when there's a really strong wind, the blade bends, and eventually the blade will hit the tower and it will destroy the tower completely. So that is the reason there's the tilt angle. Okay, now you know that the main shaft is 4 degrees tilted. The bearing configuration is usually 2 cylindrical roller bearings. What that means is that these bearings allow free bending of the shaft. So the bearings do not carry any bending load. So they will allow the main shaft to bend freely between the bearings. That is important for your calculation because you don't need to take into account the stiffness of the bearings. So you can just assume that this is simply supported shaft, like you have done in the calculation of basic mechanics. Another information for you is that the gearbox side, so is in big picture, the right-hand side bearing is the one that is axially locating. Usually both of them are not axially locating because that would then cause internal stresses, for example, due to thermal expansion. If the shaft is expanding and both of the bearings are axially fixed, the shaft will of course try to pull itself against both of the bearings, inducing quite high stresses. So therefore usually another bearing is axially floating, and in this case it's the front bearing here. And that it means that when the rear bearing here in the right hand side is fixed, all this shaft length with the hub and blades and all can freely extend, and the position of the front bearing is slightly moving due to the temperature variation. But what that means to your calculation is that all along the shaft until this right hand side bearing, there will be axial force, because the axial force is carried by the right hand side bearing. And in here you can see the designation for different dimensions. You have individually been given dimensions. So if you look at the Moodle, this project work, you can find this Excel sheet showing what is your value for each of the designations, including also the mass of the blade and mass of the hub. And also what you need to know is that your blade length, that is actually, did I change it? Yeah, I changed the blade length, so I need to change it here as well. E was now 60 meters. So I will change this in the presentation. But the length is measured from the main shaft center line. And what is important for you to know is that the blade's center of gravity is at a distance of 0.3 times E from the main shaft center line. That information you will need to know when you start calculating the torques and the bendings for the shaft. And also the masses for the blades and the hub are given individually. For material, you know that the material for the shaft is 42 chrome molybdenum 4, and for that, depending on the shaft diameter, you will have different values of strength, both the yield and both the ultimate strength. And from this calculation, you will need to do a report, and I will advise you to do the calculation only with MATCAD, because the calculation is such that you have to define the diameters. And if you do it by hand, you will have to do the calculation many times, because the calculation requires iteration. When you do it on MATCAD, you can just simply change the input values and see what is the result. So it's far more easy. I don't say that you are not allowed to do it by hand also. If you really insist, you can do it, but just prepare to be doing quite a lot of work. So I will strongly advise you to use the MATCAD. And also in the MATCAD, you can perform the report in the same file. You don't need to do any other, and actually I don't want you to do any external other Word report. You can put all the explanation with the text and figures in the MATCAD. And the report needs to include, of course, the description of the tasks, the input values, any explanation text and figures you would need. Just plain list of calculation equation following each other, it's not enough, because you need to explain what you are doing and why. You need to present bending and shear force diagrams. And for the elastic notch factor definition, I want you to use the eFatigue calculator that was shown from the web page, and include the screenshots of these results in the report. If the eFatigue doesn't work for some reason, then okay, you can use tables as well. But also in that case, you need to include the table and include in the table a drawn line in the report which shows that what is the how did you get the notch factor from the table. So it's clear for me when I read the report. But it's better to use the eFatigue, because from there you can just take the screenshot and that's it. And very important part of the report is the final results and considerations on the result, and maybe possible recommendations on the design, so that you think and evaluate what did you calculate and does it make sense, and if it doesn't make sense, why, what would you change, is there something that's maybe not reasonable. Otherwise, you should follow normal rules about scientific reports. So you have a cover page with your name and student number, you have headings, etc. So it's looking like a real report. You have roughly 6 weeks time to do it. So return it by end of April. And if you return it later, it's possible, but keep in mind that then I will reduce points from it. So late returns will reduce points. In this exercise, there is maximum of 100 points, and as stated in the grading rules of the course, you need to obtain at least 50% out of them in order to pass the course. But of course, you need to pass the exam in addition. But separately from this project work, you need to gain at least 50%.
So you said that you want us to make the report like in formal style, so we need to use Word documents, not only put text in Mathcad.
But you can do the formal text also in the Mathcad because you have the text box availability in Mathcad.
Yeah, but it's kind of complicated to. Well, okay, I think it's the less important detail.
I don't know, is it? At least I think that it is not complicated because you just input the text box and you can make the headings and you can make the plain text and whatever you need. Also in the Mathcad.
But okay, but we can't make a table of context, can we?
Yes, that is not coming automatically, but that is okay. That's a good point. You don't need to do the table of contents because I'm not sure. It could be that Mathcad doesn't provide automatically. Yes, Jaakko, you can include tables, yeah, but table of contents, meaning the sisällysluettelo, it doesn't come in Mathcad automatically as it does in Word. So you can neglect that. You don't need a table of contents. I can include that statement here in this presentation as well. But otherwise, I think it's fully possible. At least I've done reports with Mathcad with a complete similar lookout as with the Word. So I think it's possible for you as well.
And can we sometimes like ask you for help or advice, or we should do it like 100%?
Yes, that's actually good question. There's usually been some hours of my lectures assigned for helping you out in the project work. So now my question for you would be that would you prefer that there's one single 2 hours lesson which we are going to use for this project work, or would you prefer that there's maybe half an hour of guidance time divided over, for example, 3 weeks or 4 weeks? Which would you think is most beneficial for you?
I like personally, I like more the last option.
Yeah,
Yes,
the last option, same for me.
Okay, let's do that. So we can split the rest of the lessons in a way that we will have some time, 50 minutes, 20 minutes, maybe even half an hour for your questions about the project work. Let's do so. I think that's maybe the better way. So we can distribute the time along your work. And as you can note, the time for your project work, it's extending beyond the final exam. So the final exam is it's in the last week of April, and you will have until end of that week to return the report. And maybe we can also, with the Zoom, we can perform this personal breakout room, so I can guide you personally if needed. Okay, but for the blade assembly load case, what is the first one? As I described, the blades are brought into the wind turbine in horizontal position, which means that when the first blade is brought in, it's done like presented here in the step number 1. Then this first blade is then turned. The shaft is turned in a way that the first blade is in actually that is, yeah, it's in 30 degrees angle to the vertical, which means that the next interface for the second blade is in horizontal, and then the second one can be brought in. And then again, this set of 2 blades is turned so that they will both be oriented in this way, like in the step number 3, which means that the third interface is in horizontal position, because the angle between them each blade is of course 120 degrees. And now the most stressful situation for the main shaft is this step number 3. When you have already the 2 blades are installed, they are in this position, but the 3rd blade hasn't yet been brought in. Because when you bring in the 3rd blade, that will balance the shaft. But before it's attached, it means that these 2 blades, they will introduce fairly high torque to the main shaft. That it's actually so high torque that it can be, and it usually is, higher torque than the nominal operation torque. That is coming from the masses of the 2 blades. And this is the situation you need to consider in your load case 1. What are the loads to the main shaft due to this load step? So what you need to do, you need to calculate all of the masses, the blade masses, the hub mass, to loads on the shaft, bending moments, torques, axial and shear forces. And one might think that it's fairly easy to do, yeah, maybe, but you must keep in mind that the shaft is tilted. So it's backwards tilted 4 degrees, which introduces somewhat complexity to the calculation. And then when you have calculated these loads onto the shaft, then you do the static analysis onto the shaft. You calculate the stresses. You include the notch factor. And as I explained, please use the E-fatigue calculator for determining the notch factor. And in the report, put this kind of screenshot of the page in your report where you state what are your input values and what is the resulting KT factor. And the same, of course, for the other loads, also for bending and torsion. So then I have clear picture how did you obtain these K values. And what you need to do, you need to define the D1 and D2 diameters and the corner in between so that you can calculate the stresses. There is only one restriction on the diameters in a way, that in order to be able to secure the bearing raceway proper way, this diameter D2, it has to be at least 3% bigger than the D1. It can be also far bigger, but it has to be at least 3% bigger than the D1. And what you need to note is that when you calculate the bending stresses, this journal where I want you to calculate the stresses, it is not the same as the bearing location. It is slightly aside from it. Last year, majority of the students.
I don't know if I'm the only one who had the
No,
problem.
you're not.
Your voice is freezed. Yeah, Tuomo, your voice is freezed.
Yeah, Tuomo, majority of the students, and then nothing.
Hello, can you hear me?
Yes, now
Yeah.
we can. The majority of the students.
Okay, so majority of the students calculated the stresses exactly at the bearing location, which is the support, of course. Like you consider this is basically a beam with the 2 supports. They calculated stresses for this bearing location and then did the further calculation. But that is not the location of the journal. The journal is slightly aside. And that is the location you need to define the stresses in. Keep that in mind. And you have to define the diameters D1 and D2 and also the corner radius R such that the safety factor with respect to local yielding in this radius R, using von Mises, of course, it is between 1.4 to 2. It shouldn't be less because then it would not provide sufficient safety, but it shouldn't be more than 2 because then it would be far too expensive. So we want to keep it in certain range. And also you need to calculate the total twist in degrees for the main shaft, that you also know how to do it, and the torsional rigidity kilonewton meters per degrees for the main shaft. That is also fairly quick and straightforward calculation to do. So that is the load case number 1, the blade assembly. Then the load case 2, which is the operation, which means fatigue situation. Here we have dynamic loads. And loads for fatigue analysis are given in this table. So you will have bending moment, which is acting around the y-axis shown in here is the picture. So it's sort of the horizontal axis. And there you will have certain mean stress, maybe. That is something you need to define yourself. What is the mean stress in that situation? And in addition, you will have a bending amplitude, which is going to be the sum of the following. The sum of the masses of the components, hub and the blades, of course. And remember, now when it's operating, you already have 3 blades attached, of course. Mass of the shaft you can neglect. Plus, you will have plus minus 150 kilometers from the wind that is acting on the hub. That is also bending the main shaft. And these two, as a combination, will provide the amplitude for the bending. And then for the torque, you will have a certain mean torque, which is for everyone, it's 1800 kilonewton meters. And also you will have amplitude for the torque, which is plus minus 700 kilonewton meters, and that is also the same value for everyone. And how to do it? Similarly as with the previous lecture calculation, you transfer the loads from here. You transfer it into the stresses, and you remember to include the fatigue notch factor. And also remember, as we described, you had to calculate the von Mises stress amplitude and von Mises mean stress. So that because you have different stresses, you have torque stress induced, you have direct stress, bending normal stress, etc. You have to combine those using the von Mises. And then you will apply the same procedure as in the last task assignment, infinite lifetime method, Goodman equation. Please use the Niemann-Winter equation for size effect, as we use also in this last calculation example. Ambient conditions given is that there's no corrosion environment, and the operation temperature is from minus 20 to plus 35. And then you, as final result, you should calculate the safety factor with respect to infinite lifetime in this Journal D1, D2 corner. In real life, we would also calculate it in several other locations, but in this course, we only do it for that specific location. Okay. Does it sound complicated?
Well, a little bit.
Yeah, usually it does, but it opens the best when you start doing. You don't need to. Don't think that it's a big mountain that you had to leap onto the top right with a one leap. Take it a bit by bit, and then you will eventually be at the top. Basically, all the information that you will need is something that's been either you've learned from other courses before, or you've been given in this course. Basic mechanics and a little bit strength of materials and a little bit something more from this course. Are there any questions to it at the moment?
I'd say it's clear so far.
Okay, good. And let's take these supervision times at the lectures at some point. So now we can move on to the actual topic for today. It is possible that we cannot fulfill or go through all the material today, but then we need to continue next time. So the topic for today is screw joints. Last time we discussed about the infinite lifetime fatigue calculation that we cover pretty extensively now. And then the learning target for today and for this lecture in general would be to gain competence in different kind of types, different uses and application of screw joints or screws in general. And that you would understand the pluses and minuses, pros and cons of a screw joint as a fastening method in comparison to other joint types, and that you will understand the balance diagram of pretension screw joint and understand the effect of the clamping length onto the screw loading and how the joint is behaving. So I think everybody is more or less familiar with the screws. So you can find screws used in different kind of purposes. By far the most important in the mechanics and I would say the original way is the fastening screw. So you just attach components to each other with the help of the screw and the nut. Also you can use the screw as a motion screw, which means that you will convert rotation into linear movement or linear movement to rotational movement. And also when you do this movement conversion, you can convert also torque to linear force or linear force to torque. This has been used, for example, linear motion screws, ball screw, linear motion ball screws, like in grinding and milling machinery, or for example in a worm gear. There you convert the torque and force also. Fastening, tightening. Sometimes fastening, the more important factor is to tighten something, like a shaft nut. You will tighten the bearing in its location with the shaft nut. You can use screw as a plug, like an oil plug of an engine, or you can use screw as a setting screw. So you can define certain position, like here in the alternator belt. So you have a setting screw which you can use to tighten the belt into correct tightness. Or you can adjust a flagpole into vertical using these screws. Or you can align the machinery base plate with these leveling screws. This is the I would say quite common way of founding machinery in the industry. So you have a steel base plate where you need to attach some machinery, motor or pump or whatever. And the steel base plate is attached on leveling screws. And with these leveling screws, the base plate is adjusted exactly on the plane, horizontal plane. And when the leveling is done, then this space in between the base plate and the foundation of the building is being filled with, for example, with a concrete or epoxy or some other. And then there are also anchor bolts which are used then to fix the machinery onto it. Also, you can use it as a force multiplier, like a screw jack, motion screw, turning machinery, and a differential screw. So where you can obtain movement reduction or increase, usually reduction, and by the way, force amplifying effect. This is used in, for example, in a micrometer screw, like in the picture below. So you have basically two nested threads, so they are inside each other. So while if you rotate this green part handle, it will eventually cause that this blue shaft will turn inside the green part because there's thread and this rotation of the red pole of the shaft is prevented, so it moves only in axial direction. This green part will force through the screw, it will force this blue shaft forward. But also there's a separate thread between the green part and this gray sleeve. And that is also affecting to the movement. And that has opposite thread, so the counterclockwise thread on the gray part, and there's a clockwise thread on the blue part. And eventually the movement, total movement of this component is then the sum of or difference between the pitches of threads 1 and 2 per turn. So therefore we can define very little movements axially, because it would be like in a micrometer we need to have very little movement per turn, maybe one microns, and it is not possible to manufacture that kind of thread just by using one thread. But with a combination of 2 threads we can make that possible. Okay, then for the fastening screws. Of course, there are multiple benefits out of using screws as fastening element. It is easy to assemble and it's possible to open the joints. Components are standardized, very good availability. There are different kinds of materials, different kinds of coatings for various loads and ambient conditions available. And one of the main benefits is that it doesn't require that specific tools, especially when the sizes are fairly small, like lesser than M24. The tools are usually quite easy to obtain. And also one of the benefits is that when using screw joint, you will have a good compression force control in the joint. But that is sort of on the condition that you will have good design and you will have good tools for it. So you cannot obtain that with just using bulk screws from the shelf. So it requires a specific design, but it's possible. The drawbacks of the screw joint is that the thread itself, it consists of multiple notches. And of course, as you know now, these notches will increase the stress in the structure. And therefore, it will eventually reduce the fatigue strength. In this regard, the inch thread profile is slightly more shallow than metric, which means that the inch thread profile is slightly better regarding fatigue. That is sometimes the argument that the Americans are using when they persistently stick to the inch system. But yeah, okay, it's a fair argument. It is there, but is it really relevant? I don't know. To me, the American system of the threads it's been always quite difficult to comprehend. The drawback also for a screw joint is that the reliability is dependent on various factors which are not that easy to control. So the reliability of the screw joint depends on the pretension force which we obtain while tightening. And the pretension force is dependent on the tightening torque. And the tightening torque is then dependent on the friction between the surfaces. And these frictions between the surfaces in the thread and between the bolt head and the material are quite difficult to control precisely. So therefore, the key factor that we would need to have a reliable bolt joint is quite difficult to control. And another drawback is that even though we would have a preload control in order, and in good condition, we might also need some other methods to prevent the loosening in dynamic loading conditions. So this secured pretension force is not always enough. Also, one of the drawbacks is that very large screws can be very expensive and are very expensive, and for those also the tools are very expensive. And also one drawback, if you compare it, for example, to welding joint, is that you will need more complex, fairly precise manufacturing, meaning machining, in order to perform this joint. For a welding joint, you just need a couple of plates with flame cut edges, and that's it. If you put it with the bolts, then you will need machining and small geometries, therefore being a bit more expensive.
Excuse me.
Yes, go ahead.
So the reliability of the screws depends on the tightening torque, isn't it? And
Yes.
so when I have internship, I go to the assembly hall part of the company, and they have some kind of screwdriver that like can tighten at exactly the tightening force torque. Like they just defining first the tightening force, for example, ball 6 or 8, and then they just tighten at exact tightening torque. So is that like?
Yes, I know. I understand what you mean. You can have a precise tool for the tightening torque. So I believe it was hydraulic tool. Am I right? Or electrical torque?
No, it's like the micrometer. So when we over torque, the tools get some sounds like micrometer, and they just set it like mechanically. Not, I don't think that there's something hydraulic.
Okay, so it's just a manually used device.
Yeah, and they just they have some kind of rings, so they just rotate the rings to the exact torque rate, and they just tighten it when as soon as they hear the sound, and they stop.
Yes, okay, yeah. So there's a special washer under the nut or under the bolt head, which indicates when the torque is reached.
No, I mean that the rings in the driver, it is not in the joint, but in the driver.
Okay, so it was in the tool.
Yeah.
So but also that is when you have this kind of indicator in the tool, in the tightening tool, it will only indicate that the tool has reached the torque. But it is not a guarantee that you will have the torque in the screw, because you could have different frictions between the thread and the component and under the bolt head. So still there is this this uncertainty about how much of the torque you can really get to the bolt, because quite much of it will go to the friction, and the friction is something that it's difficult to control. Your tool can be very precise, and that can precise very accurately, but it is difficult to define that the friction is constant, so that you can make sure that there will be exactly the preload in the bolt that we want. There's a slide of it in the later stages. We can look further into it. So basically, you could say that applying a tightening tool, rotational tightening, it's never very accurate. It cannot be because it requires so accurate knowledge about the friction.
Yes, thank you.
Okay, so the friction joint is one type of the joint that we can utilize, and in machinery, this is quite typical. And the basic idea in the friction joint is that the shear forces which are acting in the plates, like here you can see the top plate, the gray one, is loaded into the right hand side. So there's a force acting to the right hand side, and in the lower plate there's a force which is acting to the left. So there's a shear in between these plates. And the idea how this joint type is working is that we preload this screw so that there will be enough friction between the plates that will carry the shear. So there was basically no shear at all on the bolt, because all of the shear is carried by the friction between the plates that are being compressed with a screw. And the benefit of this is, of course, that the external shear, these red arrows, they don't induce any additional shear to the screw. So the screw is not loaded by this external shear. This external shear is carried only by the friction between the components. And of course there is shear stress within the screw, but that shear is only the portion that is coming from the torque shear that is remaining after the tightening, because it's been torque tightened. There is some residual shear because of the tightening in the bolt. But this external load doesn't induce any shear onto the bolt. This is one type of the joint that we can utilize. Another type is so-called bearing type joint. And the bearing type joint is a type of a screw joint where the load is transferred to the screw. So unlike here, where our bolt doesn't see any shear force, in this bearing type of joint, the bolt is the one that is carrying the shear force between the components with the shear stress in the bolt. And if this kind of bolt is used in machinery, typically these bolts are precisely machined. So they are more or less customized so that there is a tight fit between the bolt and the components. There's interference fit to the hole. And the reason that is the case that we need for the machinery is that if we do this kind of joint with the free holes, normal free holes, so that there's a clearance between the bolt shank and the hole edge, it will mean that there is some sliding needed before the bolt can carry the load. So if you look at this lower picture, and there is some clearance between the shank of the bolt and the free hole, you understand that before the bolt can carry any load, these clearances have to go to zero. So when the load is in these two plates to the right hand side, there has to be contact between here and here. And also to the other side, there needs to be contact over here. So therefore, there will be some sort of sliding needed before the contact can be reached. And in many cases, in machinery, this sliding small movement of the components, it's too much. We cannot tolerate movement of, for example, 1 millimeter or 1.5 millimeter between the components. So therefore, this bearing type joint is not that well suitable for machinery if it's not done with the interference fit special joint bolts. But with the clearance hole, it's not very usable. However, these kind of bolts are being used frequently in I would say, in not that critical applications, and also in steel structures. In steel structures, it doesn't matter that much, even though if there would be some little movement between the components, you can hardly notice it. But in most cases, in machinery, we want to have the components precisely as they are. Okay, then what happens when the screw fails? So it's easy to understand that the tensile strength of the screw, it has a dominant effect in the screw breakage, because its tensile strength defines the maximum achievable pretension. And when we have a larger pretension force, we can also have larger load capacity. And when the screw fails or breaks, it can happen in various ways. It can break at the minimum cross section, like here in the picture over here. And this is also in the location of first loaded thread. In the bolt shank, the diameter is bigger, so of course it doesn't break from there. It's breaking from the location of the smallest diameter. Or we can have a situation where the thread is sheared off in the screw shank, like here. So the thread has been sheared off from the bolt. Or the thread can be sheared off from the nut, like in this case. Which of these you would prefer? If you could design the component, and you should design the component in a way that you define where the bolt is going to fail, which of them you would prefer?
Maybe shearing off, because, well, it looks safer than just breakage in the narrow section.
Can you describe why does it seem safer?
Well, because there still might be some contact between components, and if you have just a screw torn apart, so the whole component, like not the component, but the whole structure or machinery or whatever may fall apart too, or create some void space, which I think is not there.
Any other ideas? I think your answer was right. No problem with that. But isn't it so that it kind of depends on the design? So if you consider, for example, this kind of bolt here, which is probably this is a fixation screw for cylinder block and head. If this bolt would break, or the joint would break so that this thread is sheared from the cylinder block, what that would mean?
Replace the cylinder block or screw the new hole for the screws?
Yes. So that would be disastrous. You had to take the whole block to the machining shop and re-drill the hole with a bigger diameter and make a new, use, for example, helicoil substitutes, or maybe even bigger thread diameter. And it's very difficult to replace. Where if the bolt breaks like here, you can try removing it and setting new component instead. And the same applies, for example, if you have a joint with a nut. When the joint breaks so that the thread is sheared off from the nut, but the bolt would be quite okay, you just replace the nut and that's it. Quite easy. So it kind of depends. What is the characteristic of the joint, that what would be the beneficial way way of breaking the joint. That is something that you also need to sometimes consider. What you should, if the hoops happens, what would be the least difficult consequence of these hoops? How about if you have this kind of bolt and it will snap so that this breakage point would be inside the hole in the cylinder block? How could you do? How could you take that away?
A drill or a reverse, what's that? A screw extractor, which is the reverse thread.
Mm-hmm.
But yeah, the green one is probably the best if the brake is not in the position where it's fixed somewhere, so it's not on the thread. But it looks kind of violent, so I think of it that if it happens more gradually and little by little, it doesn't break anything else. But if it's in a small time window where the actual action of braking is very violent, it might break something else, and it would be then harder to fix. So probably the best
there could
one.
be
Best one
secondary consequences.
Yeah, the best one would be probably that the green bolt shears the head off and not break in the middle, but shears the head off so that pin would be in place, but it wouldn't have any pressure on it anymore, so that would be the only loss. So, but yeah, it so much depends on where it is and what's it doing. So if it's if it's on the cylinder block and all four go like that, then the whole cylinder block flies off the hood of the car, and yeah, that's not good. But if it's on the suspension and it happens gradually and then it breaks all the nuts on the suspension and then they break all and the whole thing just collapses, then that's not good. But yeah, it depends on where it is and what's it doing.
Yeah, that's the main point here. You cannot always say that it's the best that the bolt will shear off. It is the best that nut will shear off. It's the best that the bolt shank will break at the middle. It depends. Okay. So also the ways of the breakage of the bolt is that if you have a too large pretension, you can break the bolt by that. You can overload the screw so that it will instantly snap. That has happened. So then you know that you tighten too much when you hear the snap, and then there's no more counter torque, and then it's a whoops again. But then also, if you are still within the range that you didn't completely snap it, but you are quite close to the yielding of the material of the screw, there could be that there's a relaxation of the contact surfaces, and that will over time lead to a reduced pretension. But the relaxation only happens when you have tightened it very close to the ultimate limit of the bolt. Steel material doesn't relax, or it doesn't have this kind of I don't remember viruminen in English, but nevertheless creepage. Yeah, it doesn't steel doesn't have creepage unless you are very close to the yielding point of the material. But that will eventually lead to reduced pretension. But nevertheless, you should be tightening that bolt enough, because the sufficient pretension, it's critical for the joint for the whole lifetime in many aspects. And here in this lower picture, you can see a example of how the load distributes in a UNC 7/8 grade nut. So this is roughly, in the size, it's roughly equivalent to M24. And what you see here is that the first thread is the most loaded. More than one third of the total load is carried by the first thread. And that is the reason that we can see here this kind of breakage. So this one has been the first thread, it's the most loaded, and then snap. The second one is 23%, and together the first and two will carry more than 50%, nearly 2/3 of the overall load. And that the rest of the threads, they have less significance in the load carrying. That is good to keep in mind. But of course, we can use some other additional means how to distribute this further on. If the counter material is soft enough so that the counter material will start to yield from the location of the first threads, that will help us to distribute the load further along. Or we can use special size, specially shaped nuts, which sort of relieve the stress on the first thread and distribute the load over to the following threads. But in a normal type of joint, this is the distribution. Then something about the screw materials and grades. And of course, the strength of a screw is proportional to the ultimate strength. That is quite obvious. But in the screw materials, they tend to be quite hard usually, which means also that they're fairly brittle. And depending on the application, you have to also make sure that there's enough ductility. So it's not always a good idea to use the most highest strength bolts, because they will also have least ductility if something happens. Usually, the screws are out of carbon steels, somewhat alloyed steels, and the strength grade with the bolt is given with 2 numbers. And the grade designation is built in a way that the first number, that will indicate the material's ultimate strength divided by 100. For example, you can see a bolt head with 8.8 stamped on it. That will mean that the first number 8 stands for 800 megapascals of ultimate strength. And then the 0.8 after it means that the yield strength relative to this ultimate strength is 0.8. So we can, with this designation, we can directly see what is the ultimate strength and the yield strength of the bolt material. So the ultimate strength being 8 times 100, 800, and then the yield is 0.8 times 800 is 640. And the same procedure applies for other bolt grades as well, like 10.9. Ultimate strength is 10 times 100 megapascal equal to 1000 megapascal, and then the yield strength for the material is 0.9 times the 1000 megapascals. But this designation system doesn't apply to stainless materials. They have their own designations. There are different grades of stainless. There is A1, A2, or A4. And depending on the number, which is after the A, that will specify what is the ultimate strength and the yield strength of the material. If there's 50, it means that the ultimate strength is 500 and the yield strength is 210. That is not anymore, this designation doesn't give any hint what is the yield strength. It only gives the indication of the ultimate strength that applies to the stainless steel grades. Usually these 50 grade are not that often used, so the most often used stainless screws are A70 or A80 in the most common applications. Then there are other designations as well for SAE grade, American ASTM, etc. But we don't go into that here, because in the Europe you hardly ever find these. Okay, so it's quite obvious that when you apply stronger grade, you will have possibility to reduce the number of components. quite obvious. But when you use these grades that are higher than 8.8, you must remember that this fracture at elongation at fracture is much smaller than 8.8, and that is the reason that Eurocode 3, which is the code for generally for steel structures in Europe, it doesn't allow grades above 1.9 to be used in those structures. Another point about why not using the high strength is that if you go especially to 12.9 grade screws, and especially if you go to very large sizes like more than M24, they are not that common and they are much more expensive. They can be really expensive. Otherwise, screws are fairly inexpensive all the way to the range till I would say M40. 8.8 in the range of M40 is still quite reasonably priced. But if you take M24 in 12.9, that could be quite pricey. So therefore, it's from economical point of view, it might be more beneficial to use a larger number of 8.8 bolts than a small number of 12.9 bolts. And what is important to know about these materials is that if you have zinc, if you have availability or somebody is providing you zinc-coated 10.9 or stronger bolts, you should avoid those because they're so-called hydrogen embrittlement. You can further on, later on Google what that means, but it will sort of increase the risk of sudden breakage of the bolt. So the coating process into high-strength steels causes the hydrogen to make the material more brittle, and therefore it should be avoided. But there are other coatings that you can use quite safely for 10.9s. There are zinc flake coating, delta coating, numerous. But if you have a plain zinc, don't apply that to 10.9s. Okay, now we are a couple of minutes over time, so I think that we'll stop here for today and we continue next time. There's half of the material still left. So that was all from today. So get to know to this project work task assignment. If you have any questions, please send it to me, or maybe the best would be that you ask them next time during the lesson so that everybody can hear the answer. And you can start already doing that by your own. Okay, see you next week.
Thank you.
Thank you.
Thank you.
Bye.
Kirkkonen Disco.